Okay, so welcome to the quantum mechanics course, second lecture. For the first lecture, I'm acquainted only with Nitai Joseph. We'll go to the list. Please, could you give me your name?
Anat.
Anat. Please?
Jonathan.
Yes.
Jonathan. Is there?
Yansuf.
Jansen, yes.
Eliana, but it's not on the list. I got permission from the head of my program to sit in on one of the classes. I talked to her earlier today. Her name Elita. I don't know what her last name is.
So you're here in an exchange program?
Yeah, I mean the gap year program, the Israel Speed that Barilan runs.
So you have training in physics?
I'm gonna try. I'll leave if I can't do it. It's okay.
Okay, so this is the second lecture, and in the first lecture we made our acquaintance with several concepts in quantum mechanics. The first one was the wave function. I hope that those that weren't here physically in the first lecture did listen to the recording. Is that the correct assumption?
Yes.
People are.
Last year recording.
Mm-hmm.
I heard last year recording.
Okay, let's hope that it's clear. Well, quantum mechanics didn't change so much during the last year, but I don't remember what I did in the first lecture a year ago. Okay, so we have a wave function. What is the content of this wave function? I know that you know.
What do you mean by content?
This is a mathematical function, but what does it mean?
That's the probability density squared. No?
Well, if you square it, it will be the probability density.
Yeah.
At the moment, this is the probability amplitude. What does it mean? If I want to know what is the probability of finding the particle at point X at time t, I have to square it. Absolute value squared. Why do I insist on absolute value?
Because it's complex number.
It could be a complex number. It's not necessarily a complex number, and we'll see during this lecture when, perhaps some clue when it is and when it's not. But in principle, it could be a complex number. Therefore, a probability has to be a number between 0 and 1. Therefore, it has to be absolute value squared. Okay. Another thing that we talked about in the previous lecture, when I'm doing classical mechanics, what do I need to know about the particle in order to give a prediction where I'll find it at some later time?
Initial conditions.
Which are?
Its initial space based on the time.
X and t. is like, sorry, x and p. The momentum and position. If it's three-dimensional, so they are vectors. So I'm missing something here. Psi of x. What happened to p? Well, there's nothing holy about x. Although probably till now they've seen only psi of x. I could have written, and everything else will be the same. It's a probability amplitude, and the probability of finding it at momentum p time t how do I translate this wave function to this wave function, which the technical term is representation?
You said there was an algorithm that we haven't seen yet.
Exactly. I'll give you even a clue. This algorithm in this case would be a Fourier transform. But there's always an algorithm to translate from one basis or representation to another. Okay, so back to this guy. Well, it's a function of x, and if I want to know something about the momentum, I'm not interested in the position, but I'm interested in the momentum. So for every physical quantity that I have, there is an operator. Which is a physical quantity that we usually write down as some letter, depending on what physical property it is, with a hat on it. And we gave a dictionary of operators. So for the position, the operator is simply x. For three-dimensional position, and for differential operator. And then there's a physical quantity. And for any other physical quantities that we may be interested in, we'll have an operator that represents. Now you can come and say, why are these operators simple? Say x, and this operator is complicated, a derivative. Someone can guess?
Because once we made a measurement, right? Wave function collapses, and then we have a...
No, much simpler. This dictionary is correct for this representation, where we write down psi as a function of x. So anything that's connected with x is simple. Why? If that's not just the representation that we chose. If we are trying to represent, to get an operator for p, it's more complicated. It's a differential operator. If I would ask how this dictionary translates into this representation, will be the other way around. Simple for p, complicated for x. So it's just a question of language representation. Usually we represent it in x coordinates, and this is the dictionary. Okay, lovely. What can I do with this dictionary? I can calculate, and now we're getting more or less to the point that we ended the previous lecture. I can calculate averages. So in general, I want to find the average of some physical quantity. We will see a bit further on what is the logic behind this writing. If I want to average a more complicated quantity, the nth power of this physical quantity, no problem. Any other physical quantity, let's say the variance of some physical operator, some physical quantity. How do I do it?
It's the expected value of the operator squared minus the expected value squared.
Exactly. Probability all the way through, nothing new. The only new quantity is the psi, these operators, and the rule. Everything else is probability. So it will be okay. What else are we missing? As we said in the previous lecture, initial conditions would be the wave function at time t0. We still have to discuss where do I get this. But let's assume someone came and gave it. I predict what will be the wave function at time t. Could you give us an answer?
Yes, you do transformation. Like operator.
What operator?
Where?
What computing?
Hamiltonian.
You come from quantum computing that you use?
No.
Because that's a language that they
No,
use.
Hamiltonian.
Because they are not physicists necessarily, so for them it's just a transformation. Exactly. So, what I have to do here is use the Hamiltonian in order to get the transformation. And using the Hamiltonian is our good old friend, the Schrödinger equation. Because what is the Schrödinger equation in our language? So E, we'll look up our dictionary. And the Hamiltonian, let's assume that it's some particle in a potential. Which you recognize immediately as a Schrödinger equation. So actually the Schrödinger equation is equating two different ways of writing down the energy. One's directly as an operator, this guy, and one's through its constituents, p squared, which will be dou squared to dou x squared, and the second is the potential, which is just a function of x, so it will be a simple scalar here. Something disturbs me.
It's okay.
Oh, it's fine. You're here in order that you would be able to ask questions. Okay, so that's what we know at the moment about quantum mechanics. So, how does all this connect with classical mechanics? Okay, we have here a whole new language, but we have the whole language of classical physics. So the connection is not immediate, because the whole language here is different. We are talking about something probabilistic, and classical mechanics tells us exact results. We have deterministic results, and here we are only able to calculate probabilities. Nevertheless, there is something that we can immediately pull out of quantum mechanics without solving any particular Schrödinger equation, without knowing something essential, specific about the system that will be similar to what we know about classical mechanics. And that's some connections about the averages. All that is known as equations. That's equating average properties in quantum mechanics. Anyone here has ever heard about RFS? An interesting guy, someone who's all his life was devoted actually to statistical mechanics and following any good physicist that worked on statistical mechanics. He ended his life by committing suicide, like Boltzmann. Something about the field, apparently. Okay, so when quantum mechanics was first introduced, and as a good person who's working in statistical mechanics, his first question was, okay, what are statistical properties that we continue to carry from classical physics? Okay, so let's do two examples. Average momentum. What can we say about average momentum in quantum mechanics? What is this quantity?
The operator, the differential operator.
No, what it is in classical mechanics, 10th grade physics. P over N, forget about average in classical.
That's V. Velocity.
It's the velocity. About the averages, this is simple text grade physics. Okay, let's see that we follow that rule even in quantum mechanics with our dictionary. So, to keep life simple, although no problem in doing it also for the vector form, just repeat px, py, pz. Sure.
Average is not a number, so how can you like make and not get a zero?
A very good questions, and a lot of students somehow never ask it, come to the exam and make mistakes. I've erased it. What was the definition of the operator P, and why it was so in this way, this is the unit vector in the x direction, unit vector in y direction, unit vector in z direction. Fine. So if I'm asking what is p of x, all I have to do is, okay, and I forgot here, it's a very important term of minus I h bar, and in a moment I'll explain why it's very important. Actually, at this point, we have learned something. Px okay. But if I want to write P, I have to write so I have to work on each direction separately, right? Then builds a vector out. So our average, what is it? So I average over each direction.
Can I say it in Hebrew because it's hard?
Okay.
אם אני עושה נגזרת לממוצע זה יוצא 0, כי זה מספר.
Oh.
That was
So the question was, if I take a derivative of something that's average, I get a number, and a derivative of a number is 0, right? No. Pay attention that I have here a dependence on t. I have a number, but this number can change with t. So the derivative is not necessarily 0. Okay, but what can I say? Look on the derivative of p. Let's look on p of x. And let's assume that the wave function is a regular number, not a complex number. Sticking it into this thing, what will I get?
What was the question?
What will I get? Calculating average px, assuming that my wave function is not a complex number, just a regular number.
You get a complex number.
I get a complex number. Can I have an average momentum that's complex? No. Because I measure it,
Yeah.
and something that is measured, I don't know about you, but my measurement devices have no imaginary parts to them. So what does it tell us? That if my wave function is not complex, then my average p has to be 0. Because that's the only way that I won't get an imaginary number here. If my momentum is not 0, my wave function has to have a complex part in it. So a very general conclusion out of a simple definition. Therefore, once we calculate the wave function of a particle in a box, what happens to a particle in a box? What is its average momentum?
0.
0, because it's in a box, it doesn't go anywhere. If it had momentum, so now it's here, after it will be somewhere else. It's not in a box. Therefore, a particle in a box, its wave function can be a real number. Particles that has momentum, no.
Can you repeat this?
Excuse me?
Can you repeat this, please?
Sure. Now, we have learned that an average value of the momentum for a real wave function will be a complex number. Momentum can't be a complex number. So, the only way that those two statements can coincide is one, either the average momentum is 0, 0 times an I is still 0, that's fine, or that my initial assumptions that my wave function didn't have complex component is not true. So, and then I said, let's say we have a particle in a box. What is its wave function? Since a particle in a box, by definition, the particle remains in the box. Its average momentum has to be 0 because otherwise it will get out. Because what does momentum tell us? That now it's here, later it's somewhere else. Or in other, my position changes, but if it's in a box, it doesn't change. So the wave function of a particle in a box can be real. Has to be real. And I'll give you a taste of a further thing. The wave function of a hydrogen atom. There I have a small twist. Does the average momentum of such a particle, is it 0? But it's always around the hydrogen atom. Excuse me? Exactly. There is angular momentum. So if the electron has angular momentum, the wave function has to have an imaginary part. So, okay, we'll calculate, we'll see everything, but these are things that we can learn just from the definitions. Okay, so we were at the moment trying to simplify that. What do I mean by simplify? Just do it for x, do it for y, do it for z, and then compose your vectors. Okay, so I'm doing one of them. Okay. By definition, I know the operator, I know how to calculate the average of operators, so I just write it down. What is psi? Depends on your problem, depends on your initial conditions, but in general, this is what I've got. since this is scalar, I can move it forward. The wave function psi complex conjugate times psi is just the probability density. So I can write it down the way that it's written. Does this guy depend on t? No. Rings a bell? For those of you who weren't in the previous lecture, what is this guy?
Continuity.
Power.
Exactly the continuity equation which we have discussed in the previous lecture. So, I'll substitute this guy with something that we have learned in the previous lecture, the continuity equation. Derivative of the density is minus the divergence of the current vector. So, in here, so, what did I do here? I moved the divergence before the x. So I have to subtract the additional term that I've added by that. What did I do here? anywhere that I have divergences and volume becomes surface, it's always Gauss. Okay, I'm taking it before the term. Why? In a moment we'll understand why. Okay, so if I'm writing this guy, so if I'm taking the derivative of x, what do I get? Just jx.
Yeah, multiplication.
And if I'm taking it before it, I'm getting this term. So that's all I did here. And here is the next step, moving from here to here was just using that the divergence of any vector term within a volume is an integration over the surface. And if you're not so sure about your vector differentials and things like that, it's not terrible because, except for this lecture, you won't see any more things like that in this course, because we'll mainly switch to language of linear algebra. One lecture, let's see why. But okay, so if you don't believe it, open Arfken or Boas and have a quick brush up on these transformations. But why is this? What did I gain by this? I don't know to do this. I don't know to do this integral. What did I gain by this step? One very important thing. This is current. Now, if this is over the whole volume. If it's over the whole volume, where is the surface?
It's the surface of the object.
Right, and if the object is the whole volume,
So it's 0.
the surface is at infinity. We need another logical step. Right? Now, what is the current of probability out to the infinity? Has to be 0. Why? Because probability is conserved. I have always a probability of 1 of finding this particle anywhere. Particles don't disappear, at least not at the level of quantum mechanics that we're studying here. You want particles that disappear and appear as other particles? Great quantum field theory, not in basic quantum mechanics. Basic quantum mechanics, you have a particle, it's somewhere forever. So, summing up everything, and now I'm returning to our vector. So for x I got jx, for y I'll get jy, for z I'll get jz. So together they are j vector. This relation.
That j is equal to what? To the right of the dx.
Right, we have shown it in when we handled the continuity equation in the previous lecture. For some reason I want you to come to a lecture after you have seen the previous, otherwise you get lost very quickly. Okay. Okay, so what did I do here? Here I had R, but R is 1 over M. So I just divided by M and I've pulled in the minus IH bar into the. Now, what do I see here? Let's look on this guy.
It's not. It's B.
Right? What is this guy? Yeah, but actually, right, because it takes the complex conjugate of each term. But P is a real number. Therefore, this guy is equal to this guy. Without knowing anything about psi, has to be equal. So, I don't have half of this and half of this, I just have average P here. What I wanted to prove. So if I do the average P and average R according to my dictionary, I get the well-known classical connection between momentum and velocity. Although the language here is totally different. Nevertheless, for the average P divided by n is just the derivative of average position. Okay. Yeah.
Didn't we get in the last lecture that you were making 0 multiplied by I divided by I?
So, no, it's I've erased the dictionary, but that was minus IH per x.
Not here, I mean when we did from the probability.
Divided, so you have a minus term somewhere.
Okay.
You can ask if you do another translated.
Yeah. The Schrödinger equation, it looks very similar to diffusion. נראה ממש דומה לדיפוזיה, אז זה אומר שאנחנו מניחים שהזרם פרופורציוני ליניארי.
So the question is that the Schrödinger equation in some sense looks similar to a diffusion equation. Why? Because on the left-hand side we have one derivative of time,
And the other side,
on the other side
Laplacian.
a Laplacian.
Yeah.
Okay? Well, one has to be a bit careful about that analogy. The reason is for one little additional term that appears there. Someone can guess what it is?
Maybe the function can be complex.
You have an I.
Yeah.
And the reason is because it's not a diffusion of psi, it's a diffusion in psi squared.
Yeah.
So it has similarities, but we have shown that actually the Schrödinger equation is compatible. The Schrödinger equation for psi is compatible with the diffusion equation for pi
That's what
squared.
we don't have. So, we use the continuity equation, but are we going to use like the part that said that the גרידית?
Well, at the end of the day, we won't use it directly here. Not really. The point is, and it's a very important point, is that the Schrödinger equation is a linear equation.
Yeah.
That's very important. We'll see. Okay, so another example of this relation between classical and quantum physics regarding the average properties. Let's do the Newton's equation of motion, which shows that Newton's equation of motion holds also for quantum particles as long as we're looking at the average. Okay. This is Newton's equation of motion. Okay. And this part we know how to write down according to our dictionary. What is F?
MA.
No, that's our left-hand side. What can I write on the right-hand side that won't be exactly
minus the gradient of potential.
right? Potential we know to write in quantum mechanics. We have written it several times. So it's just so the contribution of Ehrenfest. We'll do it for the average properties. And again, just not to be so cumbersome. Do it for x, y, and z. We won't do it, of course, for y and z because it's exactly the same as for x. And then we'll get this being. Okay. So I just wrote our definition of average P's. What did I forget? Shows okay. I'm looking at it and I have two functions here that might depend on T. Psi complex conjugate and psi. Okay. know anything about the derivative of psi and the derivative of the complex conjugate, so
I'm sure there's
exactly. Some good old friends, the Schrödinger equations. It tells me how it develops in time. So I'll just copy the definition of Schrödinger equation. So I'll write here on the side. So take those two definitions, stick it into here, and write down the long expressions that I get. Hopefully without messing up the minus terms. Hopefully, I think about using some functions. Okay. Now we have to freshen up a bit on our math. Let's assume I have two functions, f and g. So if I have an expression reminds a bit what's written here. because if I'm using del on del, I'll get del square, and the mixed term will fall off. Okay, someone can guess what will be the next step? Similar to something we did previous hour.
Gauss.
Gauss. Anytime you see a del of a vector, and this is a vector, can rewrite it as an integral on the surface. So our good old friend Gauss, unfortunately it's the last time we'll see it in this course. What's now? If G and F go to 0 as infinity and don't have any discontinuities or something like that, so let's stop a minute and look what we have here. Let's call this guy G. So we have exactly what's written here. Okay. The wave function, the complex conjugate of the wave function at infinity has to go to 0, otherwise an integral over psi squared won't go to a constant, meaning it's not normalizable, meaning that I don't have a finite probability of finding the particle anywhere in the system. If this function is well behaved, the derivative will also go to 0 when the function goes to 0. Therefore, this whole term is 0. Okay, so we're left with this term. I have a derivative of v times psi, the derivative of v, and the derivative of psi.
If you want the first part to be of this pattern, you need the first term to be with a minus sign. But if you take g beforehand, then we have f
I'm probably wrong about this minus sign here. So of course it has to be here.
Here, not there. So that's minus that pattern would be minus 0, that's 0.
Okay, this guy is equal to this guy, right? And what is dx times this guy?
What is what?
This guy, integral.
Oh.
The average of the derivative of the potential, exactly what appears here. Go back and do it for derivative of y and derivative of z, and you have proven this relation. The Ehrenfest theorem. Okay, so we have learned to eke out some information out of the wave function regarding to physical properties, or at least averages of physical properties. Now, if you're dialing back to what you know about quantum mechanics, what is your impression is the main result of quantum mechanics? Let's say you're standing before a kindergarten audience, well, not kindergarten, a 10th grade audience, and trying to explain them. What is the surprising main result about quantum mechanics? Let's be even more specific about the hydrogen atom.
If we look at the averages of stuff, then we get...
No, those are 10 graders. They are not very proficient with averages.
Discrete.
Discrete values of energy, right? You are drawing these circles around the hydrogen atom and saying that they have fixed energies, fixed possible energies while they are encircling the hydrogen atom. So it's a statement about what are the possible values of heat, of the energy. At the moment, we perhaps know how to write averages, but we don't have anything to say about fixed energies. Where do we see it in the whole mechanism that we gave? Okay, let's do the first step towards that. Okay, so we have the Schrödinger equation. what is the dependence of the potential?
X.
X. And it might also depend on t, actually. We don't know. Now, if we look on a special case of solutions to this Schrödinger equation, where V is not a function of t. It's known as stationary solutions. Well, what does it mean? Let's say if we're going back to the example of an hydrogen atom. So the potential that binds the nucleus of the hydrogen, of the proton, to the electron, does it depend on time?
No.
No. If we want transitions, putting in an electromagnetic field, that depends on time. So if we replay what we know about the hydrogen atoms, if there's no electromagnetic field, it will stay stationary at some energy. If there is a potential, not necessarily. If it emits or absorbs a photon, then it can change its energy. But it's not so surprising about energy, because also in classical physics, if I have a potential that doesn't depend on time, I have conservation of energy. If it depends on time, I don't have conservation of energy. Well, at least the particle doesn't have, the whole system has. Okay, so let's assume that we are considering here as a case where it's stationary. So what does it scream to us? I have a term that have a derivative in position, something that doesn't depend now on t, and the derivative of time on the other side.
Linear differential equation.
Yeah, someone.
Oh,
Separation of variables. Screams to us separation. So the solution
but this is also not for only part of the answers.
no, this is a general solution as long as V doesn't depend on t.
But you are like demand that psi will divide it to psi of x and f of t, like two different functions, not mixed.
Exactly because of this structure of the differential equation, any solution has this form. And we'll see what it means.
There is no solution with mixture of both.
No. I always can write it as a part that depends on x and a part times a part that depends on t. I'll have a superposition of such solutions. We'll see. just stick it into the equation. Okay. Let's divide by ft. At the moment, I'm assuming that I have such a solution, sticking it into the equation and manipulating it a bit. Okay? Now let's look what we have on the two sides of the equation. On this side, only terms that depend on t. On this side, only terms that depend on r or x. Okay? Now E here is not yet energy. At the moment, it's just some constant. The usual thing, if I have an equation in one parameter that has no connections to equation in another parameter, the only way that they will be equal for any value of the parameters is that they are equal to some constant. The only assumption I did, because I know already the result, is that that constant is E, energy. But we'll prove it. It's not, at the moment, it's just a constant. Okay. Let's look on the solution which depends on t. Why did I stick here a minus? No.
equation.
Okay. That's why I want you in class, because otherwise I can write down all kinds of nonsense and no one will notice. And that's that. Okay. This equation. Oh, come on.
Oh,
Yeah, we use
Yeah.
E.
Exponent
In the
to the
power.
power.
yeah.
IH E. EN.
Almost. FT.
Minus.
I, in a moment, will arrange signs. And I need a minus, so I'll
Yeah,
get
yeah,
here.
Okay.
yeah.
So that's a solution. Right? Right. Okay, so what is the solution of this side? Well, this guy has a name, it's a stationary shredded equation. This is shredded. What is the solution? Well, tell me what is the potential. We will spend quite some time during this course solving it for different potentials. Okay, so what have we learned? In the stationary case, someone with a bit of
Can I say? I mean, if we take if we square the x of x, we get 1 for this, right? Because it's a complex number. So it means that the probability is not dependent on time.
That's the meaning of stationary.
Yeah.
If it's stationary, time just adds phase here, and it has no influence on the probability. So for a stationary problem, nothing changes. It's almost an oxymoron. Stationary, of course it doesn't change. So if I leave the electron at some solution of the Schrödinger equation for the hydrogen atom, some level, and we'll see what it means further on, will always be in this level, and the probability of finding it somewhere in space will be the same at any time. Now, are there here people who are doing their degree also in mathematics? No mathematicians. What is this kind of equation? Perhaps personal knowledge.
It's a linear differential equation.
Yeah,
Like,
Can you repeat that?
yeah.
what is this something that operates on a function is equal
Yeah,
to
transform from a vector to a scalar and a vector.
so what it's called?
Hermetic transformation, like Hermetic.
No.
No,
Yeah.
it's an eigenvalue eigenfunction equation. This is the eigenvalue and this is the eigenfunction. Okay. What did you do in linear algebra all day long?
Yes.
This kinds of problems. You wrote this as a matrix. You wrote this as a vector. Is equal to a constant times a vector. Okay, let's look on it a bit more carefully. We have here psi of x. We don't have t anymore in this equation, right? What is a vector? It's a row of numbers, right? You don't agree with the statement?
No. That's really.
What's the only difference between writing it as a function and writing it as a vector?
One is finite.
One is not is countable.
Countable. So.
Even on the other has a continuum in x and you can't count because you give 2 points, there's always infinite number of points in between. What is this part? This is a differential operator. But any differential operators that you can write down in a continuum, you can write down as a matrix for a countable or a finite representation.
Can you repeat it?
Any operation that you can write as a differential operator, what does it mean? It takes a function and transform it to another function. Replace function by vector. Takes a vector and replaces it by a different vector. What is that? What takes a vector and replaces it by a different vector? So basically the structure that we have here of an operator times a function is equal to a constant time a function, in linear algebra will be a matrix times a vector is equal to some constant times a vector. So we see now a glimpse on the connection between linear algebra and Schrödinger equation and wave functions and all of this. Actually, when quantum mechanics started, the first who wrote down quantum mechanics in the modern representation was Heisenberg. And does anyone know how he called it? Matrix mechanics. He wrote it down. Well, actually, it was a bit more complicated. Heisenberg just was in the middle of his PhD, came up with this idea, wrote down the mathematical structure, and said, I don't understand what is this mathematical structure. I know it has to behave this way, but I don't know what it is. His supervisor, Born, took one look at that and told him, I don't know what is that. That's the behavior of matrices. Hence, matrix mechanics. So he wrote it down as a mathematics of matrices multiplied by vectors. Schrödinger, a year after that, came out with a wave equation, wave mechanics. Two formulations. What is the correct one? What is the connection? Dirac 1 year after it. So, well, the connection is obvious. You're both doing the same mathematics, one for a continuum, one for a finite system. That's quantum mechanics. Same behavior. So we will switch from describing things with wave function and differential equations to behaviors that are described by matrices and vectors. When will we work with one and when will we work with the other? Well, the easiest case is for cases that have a finite number of possible states, for example, spin. Have you all heard about spin?
Like the particle between himself.
You heard the beginning of it. Well, spin is a property of all material particles. What do I mean? Electrons, for example, quarks, ions, particles that are force, particles that are transmitting force do not necessarily have spins. More exact, all material particles have spin halves or multiplication of half. Others have integer spins. I can say Chinese for some pure extension. Most Chinese I'm speaking foreign language. You ever know? Towards the end of the course, you will understand exactly and even prove that all particles have to have either half integer or integer spins. We'll prove it mathematically. But at the moment, it's enough to say that.
That's the gamma question. That's the gamma function. Using half.
No, it's although you have in gamma functions. No, it's not connected to gamma functions. It's a different algebraic structure that we will learn. The important thing is that particles like electron have a magnetic moment that could be either up or down. Time-stamp constant, not important. So they have only two states when you are asking about the properties. So something with just two properties, I'll work with a matrix. The vector is a vector with two components. The matrix is 2 by 2 matrices, and life's good. So a lot of examples I'll do on these kinds of systems. Okay, where else do we work with matrices? Anytime we want to put our equations on a computer. As far as I know, no one has an infinite computer, meaning that it can store values for an infinite number of points, which is a function. Anything that you are transferring to a computer, at the end of the day, you are doing finite analysis. So again, when you're doing quantum mechanics on a computer, you try to solve these problems. Usually on a discrete structure and matrices and vectors.
But if we solve it on a way that is for continuous, can we transform it to infinite?
If it's well behaved, yes. If something strange happens, some points that you have infinities or something, you have a problem.
So most cases. Most cases.
Most cases, yes. Okay, let's see what actually the solution means. First of all, I haven't yet proven that it's energy. What? Call it energy, but it's a constant. How do I prove that it's energy? Okay, let's take our solution. Calculate the average of the energy. How do we do it? Go back to our dictionary and write it down. This symbol is extremely, this complex conjugate is extremely important. If you forget it, you'll get rubbish. Okay, and to remind yourself, T. And I'm copying the solution from here. Just copy the definition of the wave. And that's that. Doesn't depend on T. derivative according to t will give me here divided by this 1, I times minus I, 1. So I have here just E, this times this, 1. This is a constant, you can put it before the integral. This by normalization is 1. Now I proved that this constant is energy. Yeah.
You couldn't say from the beginning that E is constant and then the average is E? Oh.
Well, I started here from the Schrödinger equation that that's its meaning, but I haven't shown that that's its meaning, right?
Could you speak a bit louder?
I said that we started from the Schrödinger equation. What does it say? The operator E is equal to the energy, right?
Okay.
So if you want, I could have said that it's trivial. Prefer to demonstrate it.
Can I ask you a question?
Just a moment, let me just finish this line of it. What would be squared? Well, again, when in doubt, go back to the dictionary and write down. I times square, I'll have here minus h bar square. Dot square dot t squared again psi will move, doesn't depend on t. Second derivative will take me here down minus e squared divided by h bar squared. Minus h bar squared will fall off. Everything else is 1. Actually, n power of e to the power of n will give me the same result, e to the power of. What is the behavior of such a derivative, of such a distribution? For those of you who remember statistical analysis, statistics.
What is the question here?
What is the property of such a distribution? We calculate the moments, right? E squared e to the power of n, which is always the first moment to the power of
It's
n.
normal.
It's not. It's very unknown.
Wait.
has a connection, has a variance. What is the variance here?
No, it's zero. It's constant.
So it's constant. Meaning that any measurements that I'll do on this wave function will give me one value of energy.
Even if I have like a lot of
Any solution of this type will give me the probability of measuring E is 1. I will always measure E.
at any time.
Anytime. Well, it's not surprising at any time. The potential is stationary, energy is conserved, therefore at any time you'll measure it, you'll see the same energy. Yes?
Would the variance be 0?
The variance is 0. All of the moments here are equal to the average to the power of n.
Okay, so that's fixed because the probability is supposed to be 1.
Exactly.
So,
Okay. That's exactly. You have only one value that you can measure here, and the value is E. Okay. It looks as if this is a special property of energy. In the next lecture, we'll do okay, we'll use this exit and go down.